Welcome to January's meeting of the Mornington Peninsula Astronomical Society, and if you've not met me, I'm Peter Skilton, and some things in the news since our last meeting are shown on this first slide here. First of all, there's the green one in the middle. I'll just turn the light out just so we can see it a bit better. There we go. This green nebula here is actually glowing neon green, and actually due to neon. And what I believe it's the only neon green nebula in the sky. And the European Southern Observatory actually found, when they turned an X-ray telescope onto it, the Newton telescope, that it was two white dwarf stars that are in the process of colliding. So very shortly they should actually collide sometime in the next 10,000 years, is what astronomers call shortly. And when they do collide, they'll form a neutron star. But they're actually causing this to glow in the neon colour. So quite unusual. White dwarf stars are what our sun will become when it reaches the end of its life and it uses up all of its hydrogen and helium, and will turn into a white dwarf star. And this is two white dwarf stars that are in the process of coalescing. Over on the right hand side we'll have the colour black. These are 7 images that were taken by the New Horizons spacecraft a couple of weeks ago. The New Horizons spacecraft is the one that went by Pluto. You would have seen that in the media about a year or more ago now. Where it is out at well beyond Pluto, in fact 45 astronomical units out, Pluto's about 39, they turned it away from the Sun. And it's a lot darker there than in the orbiting telescopes around the Earth. And what they did was they tried to take a picture of the darkest spots that they could. And they picked 7 spots across the sky. Forget about the labels, they're just the labels that they gave it in this paper in the Astrophysics Journal. And from that, they've tried to work out the number of galaxies there are in the observable universe by the brightness. Now, Hubble did this, the Hubble Space Telescope did this from Earth orbit, but in Earth orbit, the sky, even for the Hubble, is 10 times brighter than the New Horizons spacecraft is seeing from out at Pluto. So this is a much more reliable result. When the Hubble spacecraft took it, the Hubble telescope took these equivalent sort of images, they determined that there are about 2 trillion galaxies in the observable universe. And the New Horizons craft, which is the more recent one, has reduced that by a factor of 10. So it's thought to be now only about 200 billion, which incidentally, the initial readings from Hubble, if you go back even further, was suggesting about that number way back around 1990. And then they revised it upwards, and now it looks like it's going to be coming downwards. So that's black. And the third image down the bottom there that looks a bit like the cork coming off a bottle is actually the SpaceX Dragon craft undocking from the International Space Station. And when was it? It was a couple of weeks ago, or barely a couple of weeks ago, on the 12th. They collected, 12 bottles of Bordeaux red wine from the International Space Station that was transported up there in November 2019 to actually see the effects of space and microgravity on wines. At the time of taking the red wine up there, they also took 320 grape plants, and they were Merlots and Cab Savs. And what happened with this the SpaceX craft is they've taken all those grapevines and also the final wine. They've brought it back down to Earth, and it's going to be a private tasting. I think they refer to it as a private opening ceremony. I'm sure it's not all going to be drunk. There's going to be an awful lot of analysis on it to see what the impacts are. Now, I don't know whether they're looking at trying to grow things like this on Mars or on the Moon, but they certainly were able to get those flown into space. Right, so tonight, welcome any new members of the Society. Are there any new members here who've, yeah, 1, 2, 3, 4. If you pivot yourself around, you'll see our new members officer at the back there. If she hasn't already said hello, she's got a hand in the air, that's Nerida. Feel free to say hello to her later, and if you have any questions, please ask any of us. But go for Nerida first. She's less aggressive than the rest of us. For those who aren't new members and are renewing this year, a reminder that renewals were due on the 1st of January, so if you haven't renewed yet, and most members will have renewed by now, please do so soon, so your years of membership count don't get reset to 0. In a moment or two, I'll talk about what the Society's been doing in the past month and what's coming up in the month ahead. Then we'll go into the main talk of tonight. Now, we don't have a speaker here in person tonight. January is notoriously difficult to get, particularly people from the university sector here, because they're still all on holidays or preparing for the future year coming up. But instead, we've managed to get hold of a talk from Monash University from the 16th of December, so it talks about the conjunction of Saturn and Jupiter, which occurred last month, so it was just a couple of days away from that, of Associate Professor Michael Brown, who specialises in galaxy studies at an observational astronomer at Monash University, and a third-year student, Krystal De Napoli, who is a Kamilaroi person from North East Victoria, I think. So she's of Indigenous descent, or at least part Indigenous descent, and they'll give a talk that was given at Monash University on the 16th. Now, that'll go for about 3/4 of an hour, for that particular talk. Then after that, Mark Stevens will come and present Sky for the Month, and then we'll break for a tea break, and then you have a choice. So after the tea break, you can either go down the observatory and have a look through the telescopes, and our members will be down there to show you the night sky as well, so it's lovely and clear out there and not too hot and not too cold. If you don't wish to do that, you're welcome to stay in here and listen to some videos that we'll put on, shorter ones, answering those questions underneath. And feel free to move between the two sessions as you wish, so don't feel shy about interrupting in here, coming in part way. Just feel free to wander in and out as you wish. So after the tea break, we'll start with an interesting one that was submitted from overseas, and you'll hear a little bit more about that one from Ethan Murphy, and you'll understand at the end of it why I've put it up. Following that, we'll cover why do mirrors actually flip horizontally and not vertically. If you've noticed when you look in the mirror in the bathroom at home, why you only see your right side appears to be in your left, and it doesn't actually flip vertically, and this explains why, if you've wondered. And then we'll look at why mosquitoes are attracted to you, and indeed I've already put on the AeroGuard because there were mosquitoes in here just before. And it will attempt to explain why they're either attracted to you or not attracted to you. And then we'll finish with a video that goes for about 15 minutes from Oxford University about how do we know that the Milky Way is actually a spiral-shaped galaxy when we're actually inside it, and certainly don't have the technology to get outside it and look back in. Then at the end of the session, as we've been doing over the last year, we'll close with a little bit of music that's been submitted by Diana Clark, musical director of the Cadence Choir in Black Rock. And this is a cappella, so in other words it's voices only, no music as such. And that will be combined with a NASA Hubble and Spitzer Space Telescope video at the background simultaneously. Moving on to the events. Now, recently, Nerida will actually recognise the photographs here because she took it. We had the Society's free roast dinner last December, just before Christmas, and that went down really well. We were at our COVID capacity for the evening for that event, and it went very well. A couple of days later, we had the anticipated conjunction, the grand conjunction of Jupiter and Saturn, that were meant to be visible. So a couple of us went to Oliver's Hill with telescopes at the foot of Oliver's Hill in Frankston, right on the foreshore. And sadly, it was well, worse than 100% cloud cover. It was drizzly, raining, and we had a couple of people walk by, but obviously they weren't going to hang around to look through the telescopes, because telescopes tend to turn into rain gauges when it's raining very easily. So the 21st was the actual closest approach to them in the sky, which is like a 1 in an 800 year event. So you've got a little way to wait till the next one. I think there's a similar sort of one about 2080 or so, but it won't be as close as that conjunction. We took pity on the public, and a couple of days later we went to Oliver's Hill again, and on the 23rd, and we set up there, and it was 100% cloudy again, but at least it wasn't raining this time, so it was much improved. So the photo down the bottom there is the 21st one, where it was a bit wet and cold and a bit dreary, as you can see by the photograph. And the one on the right is something that we didn't do with astrophotography, but on the ground. And these piled up rocks were offshore, just off the base of Oliver's Hill. And I don't know if they're actually still there. They might very well be. And there was a photographer taking pictures of that curious set of rocks that have been placed on top of each other. Now, there was no committee meeting held in December. We had enough on our plates as it was, with all the activities there, so we skipped the committee meeting, so nothing to report on that one. And then we began our first public nights back again since the COVID restrictions relaxed a bit. So the first one we had was on a Saturday the 2nd of December. The reason we didn't do a Friday is because 1st of December, some people may not be feeling too well the next day after New Year's Eve. January, oh yes indeed, quite correct, thank you very much. So where I've put 2nd of December, that indeed should be 2nd of January. Oops. Thank you very much. We had a good turnout there. There were 49 turned up, but that includes members as well. And it was under 100% cloud, so they all listened to Trevor speaking there without having telescopes afterwards. And the next one, about a week later, on the back to the Friday night, was here at the Briars as well, and we had 62 turn up. So we can't have 62 in here under the COVID regulations, so all we can have is 50, and the remainder of the members had to stay outside. So ordinarily, in ordinary times, the members can come and go as they like and listen in on the talks on the public night. But during the COVID restrictions, we're a little bit tied there if the place is full to capacity with the public. Now that one was particularly good night because there was no cloud, and it was very good steady seeing as well through the observatory telescopes. A week later, so that was last Friday, we had another public night here, and alas, the cloud was back again, and indeed there was lightning off to the north as well, although it didn't go here. Had 56 turn up, and then about 10 minutes after they all left at the end of the evening, the clouds completely cleared and the stars all came out, but alas, all the public is home. Very, very sad. Right, so coming up, we have another public night here at the Briars this coming Friday, and indeed we've got 50 booked, which is the maximum, so we should have every seat filled there. But members are welcome to come along for the outside part during that evening as well, because we can have up to 100 people outside, but it's only inside in the auditorium here that we can go only up to 50. 23rd of January, which is the day after, so this is a Saturday. We've got two things on at the same time. One is the members' barbecue here at the Briars, which usually starts somewhere around about 5 or 6 o'clock in the evening. So you'll be able to have that, and those members with telescopes that wish to help, we're going to visit the Hallam Scouts who are at the Bay Park camp at Mount Martha. Now this is next door to where the Society used to hold its Christmas function before we had the building here at the Briars, so the older members of the Society may indeed remember that particular venue. This is the camp next door. It's marked on all maps and fairly easy to find. So it's about a 5-minute drive from here, just up the road up the hill. And we're expecting about 50 scouts to that one. They're probably cubs rather than scouts, because we've done this group before and they're usually fairly young cubs. 27th, we are anticipating a committee meeting at this stage, and then on to the public night for February, which we've, I think, just about booked out fully as well. So we're at maximum capacity for the February one. And our next society meeting here is on February 17th. Now, looking further afield in yellow, we've got a school night in March down at Shoreham, and we've been to this place several times before over the years. At Aluka, it used to be called Camp Aluka, and the girl guides used to own that property before they sold it off. So we'll be looking for help for that from members with telescopes. Then a couple of days later, Dave Rolfe has arranged us for a 3-day stint at the Train and Hobby Show exhibition, which will be our very first time there. But I believe that has about 100,000 people go through during the weekend.
Is that Train and Hobby Show at the Sandown Racecourse?
I believe so, yes, I believe so. I don't know the details of that as yet, but they'll come out on the Scorpius email group to all members as we get closer. And then we've got the geology expedition down to Point Leo for members on the 21st of March, so that is coming. Now, that one had to be cancelled last year because of the COVID lockdown and then restrictions on that, but that's back on again for the 21st of March. And that will probably have a small charge associated with it because we're bringing in a geologist guide from outside, and so that will probably be of the order of, I would think, about $10 a head or something to go to that, but it should prove very, very interesting. And then we have another school night at Parkdale Secondary College. We've done the Year 7s there for many, many years, and usually ends up a very good night all round. So on to tonight's talk. With Michael Brown and Krystal De Napoli here, with Indigenous Astronomy, Light Pollution and the Shared Wilderness of the Night Sky. Now, this was done, as I said, on the 16th of December, and all lectures there were being done remotely, and indeed this one is still done probably by Zoom or whatever their equivalent tool was at the university. So, as I said, this goes for about 45 minutes, and I'll start it off now, and then at the end of that we'll move to Mark with Sky for the month before we break for the tea break.
Introduce Michael and Krystal if they want to turn their cameras on. Thank you. Krystal, who I mentioned, works with me. She's a student currently, just finishing up her undergrad. Krystal De Napoli is a Gamilaroi student in astrophysics, and is researching the ways in which her culture and scientific interests intersect. So that's a fascinating area for me. Krystal is also working on a couple of books and has a long-running interest in science communication. So you might see Krystal speaking publicly elsewhere. And Krystal has been a great addition to our new unit that I mentioned before, but also we're building an Indigenous science website together to help other tertiary educators. Associate Professor Michael Brown, welcome. Michael is an observational astronomer at Monash's School of Physics and Astronomy. He specialises in multi-wavelength studies of galaxies using large telescopes all around the world. Now, we were just talking about the large, and I'm not going to use the right technical words, the large array, the large detector that just collapsed, that you may have seen spectacularly filmed in the news recently. Obviously, he's not currently using that for his research. I will hand over to Michael and Krystal.
All right, pleasure to be here. Let me bring up my screen in just a second. All right, and let me, I hope everyone can see my slide presentation now. So it is a pleasure to be here at the end of this tumultuous year to discuss Indigenous astronomy, light pollution, and the shared wilderness of the night sky. illustrated here with this beautiful shot of the Milky Way taken at the European Southern Observatory, of which Australia is has a partnership with at the moment. And it's also a pleasure to be presenting this with Krystal, who I had the pleasure of teaching in ASP 2011 and ASP 3231 a couple of years ago. So one of the key themes that I will want to convey for this talk is that the night sky is very much a visual experience, something that you can experience with your own eyes unaided. So there's roughly 5,000 individual stars that can be seen with the unaided eye. And there's then beyond that, the faint glow of the Milky Way, which is coming from billions of stars that we can't individually see. And we can see the Milky Way stretching across the sky from Sagittarius through the Southern Cross out towards Orion. Beyond our own galaxy, you can see the faint glow of stars in other galaxies, the combined light of stars in the Andromeda galaxy, 2 million light years away, and the faint glow of stars in the Magellanic Clouds, satellite galaxies of our own galaxy. And we can see the night sky changing. So on any given night, we can see the stars appear to rotate in the sky around the celestial poles, which we now recognize as the rotation of the Earth around on its axis. And at particular times of year, we can see different stars are up high in the night sky, which we can now recognize as resulting from the motion of the Earth around the sun. So for example, in the middle of winter, Sagittarius is high in the sky, whereas when we get around to summer, in the middle of the night, Orion is high in the sky. We can also see the night sky changing throughout the year or across many years. The planets, the wanderers, move relative to the fixed stars. We can see Mercury, Venus, Mars, Jupiter, and Saturn with the unaided eye quite easily. Uranus can slip in there at a bit of a, if you know exactly where to look and you've got good vision. And then beyond that, what we have, what we also have are visitors to our night skies. So for example, there are shooting stars, which you can see on any given night, but there are regular meteor showers and sometimes even meteor storms. And there's also less frequent visitors like comets, novae and supernovae, which might appear every few years, or in the case of supernovae, perhaps every few centuries. And all of this we can experience visually, and indeed, cultures across the world have experienced it visually themselves over millennia, and it's informed those cultures in various ways. So planetary motion is very much a strong visual aspect of astronomy. So a classic example of that is Venus is sometimes the evening star and Venus is sometimes the morning star, which reflects the motion of Venus and us around the sun. Various cultures have produced models of the motion of planets around the sky, including models which make predictions about when, say, eclipses, etc., might happen, or conjunctions. So, for example, in Western culture, in Europe, the Earth-centered Ptolemaic model prevailed for many centuries. And while it gets a bad rap, it should be said that the Ptolemaic model had a lot of merits. It could predict the positions of planets, typically with an accuracy better than a degree, although it did tend to fall over a bit on Mars. And the Ptolemaic model was very much based on visual observations, observations taken with the unaided eye, perhaps using a sextant or a giant protractor effectively to measure the positions of planets in the sky. The sun-centered Copernican model that was developed by Nicholas Copernicus was designed to provide a more intuitive mathematical model of the solar system, but actually included very little new data in constraining this revolutionary model. It still used many of the observations that Ptolemy had used centuries before. Even Kepler's laws of planetary motion, that a planet moves in an ellipse around the sun, that a planet sweeps out equal area in equal time as it moves around the sun, that the period of a planet's orbit squared is proportional to the distance of the planet from the sun cubed. Those laws of planetary motion were in fact informed by visual observations. Tycho Brahe's visual observations of planets which had unprecedented precision were in fact not taken with a telescope, but were taken visually by Tycho Brahe, unaided, with effectively a giant sextant to measure the positions of planets to a small fraction of a degree. While in the Copernican revolution, Galileo's telescopic observations and his persecution by the church feature prominently, those telescopic observations which observed the phases of Venus as it travels around the sun, that discovered the moons of Jupiter, those telescopic observations were confirmation of the Copernican revolution. They weren't actually the starting point of it. The starting point of the understanding of planetary motion was actually based on visual observations, people with their own eyes observing the planets in the sky. That visual aspect continues on in many aspects of astronomy. So for example, comets are very much a visual experience. And if you've had the good fortune of seeing a comet, a bright comet with the unaided eye, it's unforgettable. Comets that are visible to the unaided eye turn up every few years to every few decades if we're a little bit unlucky. And we now know that these are dirty snowballs that are heated by their passage close to the sun. The ice is melted and evaporates on the comet, and the dust is launched into space as well. And we can get tails stretching millions of kilometers across the solar system. And so from Earth, we can sometimes see tails stretching tens of degrees across the sky. Those tails are actually not sort of something that you can really appreciate with a telescope, which takes this very close focused view rather than a broad sweeping view. And so, you know, a comet at its best is often a very visual experience, seen with the unaided eye. And I can certainly remember seeing Hyakutake back in the 1990s with a tail that stretched about a quarter of the way across the entire night sky. While some comets pass by infrequently, only returning to the center of our solar system after millennia, others do return more often. And the most famous of these comets that return relatively frequently is Halley's Comet. Halley did not discover the comet that bears his name, but instead, through hard work and understanding Newtonian physics, recognized the periodic return of that comet. So while the 1682 observations of Halley's Comet were by Flamsteed using telescopic observations, the earlier apparitions of the comet that Halley used to understand its periodic motion and return were visual observations by Appianus in 1531 and by Kepler in 1607. So Halley's work, which was one of the early and most outstanding triumphs of Newtonian physics, while it was in the telescopic age, actually was very strongly connected to visual observations taken by observers at dark sites with their own eyes without any aid whatsoever. So while astronomy has very much moved on from being purely visual observations, we've moved on to radio waves, such as at the Arecibo telescope, which unfortunately collapsed recently, and also famously collapsed on Sean Bean and GoldenEye back in the 90s. We've moved beyond the visual. We've moved to radio, we've moved to X-ray, we've moved to infrared, what have you. We've even moved to astronomy beyond light using neutrinos or famously gravitational waves coming from colliding black holes. While all of this is part of the contemporary astronomy landscape, astronomy still remains a visual experience, a science that you can visually experience in a way that you can't with some other sciences. You know, you can go out and you can see the stars if you have clear skies. You can see Venus in the morning or in the evening, and you can see that planetary motion at work. You can see stars change with the year, that's seasons. You can see the Milky Way, the galaxy in which we live, stretching across the sky. And you can see shooting stars and meteor showers and comets and novae and supernovae. And you can appreciate the planets with a small telescope in your own eye at the eyepiece. You can see the rings of Saturn, you can see the moons of Jupiter, you know, you can see the ice caps on Mars. So this is very much something that we can all experience for ourselves. And it's something that makes astronomy connect with many people around the world. Unfortunately, however, over the past century, our experience of astronomy has definitely been changing. And that's perhaps illustrated by this photo here of the Melbourne skyline. As a civilization, we've been building up lighting, and that light affects our view of the night sky. If you have a clear night in Melbourne, near the CBD, you might be only able to see tens of stars, not thousands of stars. And this is because the stars, the fainter stars, are lost in the light pollution that comes from the CBD. And even in the suburbs, you'd struggle in many of the suburbs to be able to see any sign of the Milky Way, although you can see the brighter stars within the Milky Way. Beyond that, there's also some new threats to how we view the night sky. This image here shows a very large star field. The star at the bottom of the image here is Arcturus, which is quite a bright star. And we can see here two satellites, which are part of Elon Musk's Starlink communication satellite constellation. And this constellation of satellites, just in and of itself, is going to multiply the number of satellites in low Earth orbit by a factor of several. There's going to be somewhere in the order of 10,000 of these satellites, and other low Earth orbit satellite constellations are planned. This large number of satellites in low Earth orbit could potentially, unless mitigated, impact our view of the night sky. There's a genuine risk, if we're not careful, that in the early evening or in the pre-dawn skies, that our view of the night sky will always have some artificial satellites in view. And so we'll lose that sense of pure wilderness that we have with the night sky now. And this would be an impact that would happen regardless of where you are on the globe. Indeed, for some latitudes and some times of year, it's possible that the satellites would be visible throughout the night. So this is a very serious concern about how we connect with the shared wilderness of the night sky. So a real concern for astronomers now is that the night sky has been sort of a shared universal wilderness for millennia. It's been part of many cultures for millennia, but perhaps it's going to be fundamentally changing. You know, the night sky has often been the starting point for science, a natural inspiration, a natural thing to explain. Seasons, time, planetary motion, cosmology often have their origins in our visual observations of the night sky. So what happens if that experience is lost? How do we experience astronomy if we don't have that natural connection with the night sky? What if the night sky is reduced to a few bright stars? What if our view is always contaminated by a few artificial satellites? And what if that connection with science becomes less natural and always has an artificial element involved in it? Does that lost wilderness become an issue? So at this point, I think it's probably a good point to hand over to Krystal, who's going to introduce an Indigenous view of the shared wilderness of our night sky.
Awesome. Thank you very much, Michael. That was, a fantastic introduction. And I really like the point of highlighting how something like a comet is something that it is, I guess, easier to appreciate in a visual experience, so that if you're actually using a telescope, you actually do lose something instead of, a hyper clearer image of it. So I just think that's a really nice point to make, so that even though we have technology that's always improving and increasing, there are experiences that we have that sometimes are just best left when they're in their most basic natural form. So yeah, my name's Krystal De Napoli. I've been introduced before, so I will jump into things. I'm going to share my own presentation and talk you through a bit of it. Okay, hopefully that should be showing right now. Sort of hard for me to verify, but anyway. So I'm here to talk about some Indigenous astronomy and give that, I guess, like the cultural heritage point of view of why the preservation of the night skies is very important, or at least in my eyes. So I do a lot of work in the field of Indigenous astronomy. Research with science communication is such a massive part of it, and that's to just try and educate people on a more truer and accurate history of Indigenous knowledge and culture. Indigenous science is something that tends to be historically overlooked, and that's why I'm so excited to be a part of the changes that Monash University has made in terms of creating this Indigenous science unit and making it accessible to as many students as they can. And I think that this is something that will hopefully just keep expanding in the future through all universities as well. To give some background on Indigenous culture, at least here in Australia, I think it's important to highlight a few things. And so we are said to be home to the world's longest continuing culture. This is on a scale that is just so hard to comprehend if we are thinking in terms of colonization over 200 years ago, being Australia's more recent history. When we start to think about the timescales of Indigenous culture going 80,000 to over 100,000 years in length, it's something that it's just hard to wrap your head around. And we can think of all the, I guess, all the historical events and that we attribute to the last 200 years. You can imagine just how much history and knowledge has been packed and has evolved over that time scale. So to highlight as well, I've loved to include this map. It's a map of the approximately 250 different language groups of Aboriginal languages here in Australia. And you can use that as a rough approximation of the different countries that are here on this continent. And so I think that's an important thing to distinguish as well, that these are 250 different languages, not 250 different dialects. We do have around 700 different dialects. And so these language groups, you can think of them as countries that are as diverse as any countries in other continents. So if you were to compare in Europe, a place like Germany and Italy, the different cultures, the different languages, that's the level of diversity that we see here on this continent between different groups. There are similarities and there are a lot of stark differences as well from neighboring communities. Another important point, which most people are probably already aware of, is that Aboriginal culture here is an oral culture. And so this is common for a lot of Indigenous cultures preceding the written word. So this is a culture which thrives on encoding and transmitting information and knowledge through thousands of generations without relying on a written textbook or writing this stuff down. And sometimes it can be hard for people to wrap their heads around, particularly if we have that Western bias, where it's hard for us to think of how we would trust this information to be transmitted accurately. And yet this is what we see. And so we can think then if we have 60,000 or plus years of a world's longest continuing culture, we get a really long record back, or a really long look back into history of the things that have happened here on this continent and of the way that this information has evolved over time. So to begin, so I just wanted to highlight them before never mind, I'll jump ahead. It's so weird talking to a screen. Sorry, I'm so used to doing this in person. Not seeing people's faces is a bit jarring. So I wanted to highlight what we risk losing when it comes to light pollution and cultural heritage in the skies. And this is a comparison that I love to highlight, where if the skies are our library, our books are the stars. To expand upon what I mean by this sentiment, knowledge in Indigenous culture is usually encoded into oral traditions or stories. And so a lot of these stories people tend to be familiar with in a way that they've heard about, you know, the rainbow serpent, or have been taught some sort of story in, say, primary school or in passing. And we tend to think of these, or tend to be taught them, as though these are these mythical stories that are just sort of some fantasy to enjoy. But actually, a lot of these stories are encoding information and are using the characters and the features as a way of symbolizing the information. So an example I love to give is if I'm trying to encode information about the sun and the moon, and the way the sun and the moon move across the sky and the way that they sort of interact, I can tell a story about a sun woman and a moon man. And it simplifies this concept, and it enables me to be able to encode different layers of complexity into it. So if I want to talk about the way that they pass along the sky, and I can say that I want it to be that the moon man is following the sun woman across her path, I can tell that story to a kid of the, you know, of the moon man following the sun woman. But if I want to get into some complexities about the way they move, I can talk about relative speeds, I can talk about their movements, the moon man zigzagging away from the sun woman, talking about how the moon is sometimes above or below the sun's path, which is the ecliptic. So there is thousands of examples of the way that we can take a story and we can encode layers of meaning, and we can reproduce it at different levels of complexity, depending on who we want to educate. So a lot of these stories have their reference points in the sky. So these stars, these features, a lot of them, which I'll highlight in a second, they're essentially the books. They are the reference point for a knowledge tradition, looking at the Southern Cross, for example, and knowing all of the information about maybe a particular community's calendar that relates to the movement of the Southern Cross, the information we need to know for navigation. You can encode a lot of meaning and relate it to a constellation, because it's not just a story you have to keep in your head now, it is something that you can see in your landscape, and it is easier to, I guess, trigger that memory. So if we start to obscure our library, if we start to have this increase of light pollution, we are able to see less of our stars and our features, we are starting to lose our books. And so this is why I find it really important to look into dark sky preservation. So I wanted to give a couple of examples of what I mean in terms of how we can use features in the night sky as a library or a reference of sorts. I wanted to give the emu in the sky up first, because this is a very popular example. Anyone who's seen my talks before probably knows this like the back of their hand at this point. But it is a great example of how you can use a feature in the night sky to encode many layers of knowledge. And so here we have 4 panels of the emu in the sky. And the emu in the sky is essentially where you'd find the Milky Way. So the bulge of the Milky Way makes up the emu's body. We have the Coal Sack Nebula for the emu's head. And if you go to a dark sky region, you're going to see the shape. And I love it because, to me, it actually looks like an emu. So it's a constellation that I can actually see and understand a lot more than some of the obscure ones that I've grown up learning. So the emu, if we look over here, we have this panel A. This is the female emu who is running for a mate in autumn. And so this is the start of the emu breeding season. And this is around the time of year that, at least the tale that I'm talking about, which is a Gamilaroi perspective, but it's very similar to a lot of different communities right across the continent, they would know this is the time to collect the emu eggs. There's also not obviously, but there is a focus on sustainable harvesting. So making sure that you're only taking enough eggs that you need and enough to let the life cycles continue. If we look over at panel B, this is in winter, so around June, July. And what we are seeing is the Milky Way, or the emu in the sky, sort of heading downwards. And this is said to be the male emu sort of sitting down to roost over the emu eggs. So at this time of roosting, this is actually when chicks start to form in the eggs and when people would stop collecting them. Panel C, this is representing springtime and this sort of perpendicular angle that we get with the horizon and the Milky Way. And then in panel D, this is around summertime. And what looks to be the tail of the emu sort of lowering itself down into the waterhole of the horizon. And this lowering itself of the waterhole is said to displace the water, used as a descriptor for the dry, arid conditions of summer. Then we will start back up in panel A in autumn to continue the cycle of the emu. So you can see from this one story, we are looking at a feature in the sky and we have different layers of knowledge that we can encode. So it's telling us about the emu behavior. It's talking about the seasonal change with also the water source changing in terms of its availability. It talks about our food source of the emu's eggs and also highlighting sustainable harvesting. And this is a very simplified version of this one story, and there are many, many others just like it. So you can see the different layers that we can encode. I wanted to highlight some other features in the sky which are very vulnerable to light pollution. Because, for example, like with the evening on the sky, we can't see the Milky Way in Melbourne. In my hometown, I can if I head a few minutes out of town, and I'm lucky for that. But a lot of people haven't seen this before in their lives, and yet it used to be a common, universal experience, and not just here in Australia, but in different Indigenous communities around the world, attributing their national birds to seeing the same pattern. So the Magellanic Clouds as well, they pop up in quite a lot of different astronomical traditions for Indigenous communities. They're regularly seen as birds or cranes or brolgas, and they're tied a lot to law and used as calendars of certain events throughout the year. And it's a bit sad that we are here on Kulin Nation land and they have traditions relating to the observations of these features in the sky, and yet we can no longer see them due to light pollution in the city. Comets, as well, as Michael Brown has discussed already, these also feature a lot in oral traditions of Indigenous, different Indigenous communities. They tend to be seen as sort of, so at least from what I've seen, tend to be seen as sort of like omens, highlighting taboos in society. Usually when you see one reinforcing like, oh, you know, this is a reminder for us that we act in a certain way in terms of things like generosity, I know, in the community, like not being someone who is very greedy with food and what's the word, like resources, just as an example. But also is tied to, in Gugu Yalanji traditions, it is tied to the rainbow serpent, some of their rainbow serpent traditions, which are tied to Halley's Comet, which is something that you periodically see every 75 years. And so for something like this to feature in Indigenous astronomical traditions, it's highlighting that longevity of the tradition and how encoding into stories and passing along is actually an accurate and safe way of transmitting information. And it's not included here, but I have given countless examples of traditions which have been passed along for way longer periods of time. Like 75 years is actually quite small for Indigenous astronomy. We have traditions which are passed along for hundreds to thousands of years. It's a fascinating field, and oral culture it's amazing how you can transmit information accurately. I have a short amount of time, which is why I'm sort of speeding through some things. So I also wanted to highlight a special feature in the night sky. This is found within the Southern Cross, which is arguably probably one of the most popular constellations in this country because it is on our flag, for Australian flag, and it is something that's quite unique to the Southern Hemisphere. So the Southern Cross, it has its fifth smallest star, which is known as Epsilon Crucis. And this star also has a lot of other significance because thanks to an IAU decision, I think a year or two ago, this star, this Epsilon Crucis star's official name, not its bare designation, which is Epsilon Crucis, its official name worldwide is actually an Aboriginal waterman name, Geenan. And so this star, or the word Geenan, is said to represent a dilly bag of knowledge. And unfortunately, this is one of the stars that is vulnerable to light pollution. If you go out and you try and look for the Southern Cross, this is one of the dimmest stars in that constellation. And it's a shame because this is something that's not just Aboriginal heritage here, not just a part of our constellation on our flag, but this is something that worldwide is attributed to this continent. It has its name from this continent. And it's a shame that that's something that we're losing sight of in cities. Okay. The final thing I wanted to highlight as well is how we also have certain stellar observations from stars which feature in a number of astronomical traditions. For example, here, like the Pleiades. And I want to highlight, jumping back a few slides here, this is also a painting of the Pleiades. This painting you can find on the Australian Mint's Indigenous Astronomy series of coins that they have at the moment. This is the second coin in the series, and it is for the Seven Sisters, or the Pleiades. And these stars are used by many groups right across this continent as a calendar of seasonal change and also relating to certain animal behaviors. And this is from, East Coast to West Coast. There are different communities with their own traditions. And this is a set of stars that's quite difficult to see as well, especially currently in Melbourne. And so there are certain aspects of There's certain features in the sky essentially that we are losing to light pollution, which are really important signposts and reference points for a lot of Indigenous knowledge and Indigenous knowledge systems. So sorry for that speedy version, but that is what I will share for now, and I'm happy to answer any questions on the topic. Thank you.
Thank you, Krystal and Michael. We've got some questions coming through now. Let me see what Claire has sent us. So for both of you, I guess, what's happening in the night sky now that's interesting to you? I guess at this time of year, that means.
So perhaps I could lead off with that one, since I've been asked this question a couple of times recently. So the most interesting thing that's happening in the night sky at the moment is the conjunction of Jupiter and Saturn. They're very close to each other in the sky at the moment. And tomorrow evening, if it is clear, which is a bit iffy, the moon will be directly above Jupiter and Saturn. So you can see that in the early evening, a very thin crescent moon, and then Jupiter and Saturn below. And then a couple of days later, on the 21st of December, they're going to be so close to each other that it's going to be like a fraction of the width of the moon. And that's the closest that they've been to each other and observable with the unaided eye for 8 centuries.
Wow.
So if you were to look at those with a telescope, you'd be able to see both planets together, both planets' moons, the clouds of Jupiter, the rings of Saturn in one telescopic view. So that's going to be something that I'm certainly looking forward to.
I definitely have the same answer as well. The Saturn and Jupiter kiss is very exciting. So.
Well, it's once in 800 years.
Yeah, pretty rare.
Yeah.
More than once in a lifetime.
Not planning on seeing that again. Okay, question 2. So this is from someone who is asking, if I had an interest in hearing more about astronomy and about Indigenous astronomy, where should I go?
So we have a website for Indigenous astronomy, which is an excellent database resource of majority of the resources that are out there related to this field. And so you can search via community, search via content. You can see information about different elders who have contributed to the research. And so it is simply www.aboriginalistronomy, in one word, .com.au. You can visit there and find out more information. And we also, as mentioned before, Angela and I are working on an Indigenous science database. It is for tertiary institutions. I don't know how much we can actually promote about that just yet, because it's still getting polished off.
Yeah, it's mostly for educators wanting to teach about Indigenous science, but certainly it has a strong astronomy page. Yeah. But the astronomy page has a strong overlap to that Aboriginal astronomy page too. So that's a good place to go.
Yeah.
Okay, so from Elaine, how do we manage the issue of light pollution? Is there anything we can do?
So I'm happy to sort of start with that one. So there's a number of things that we can do. And one of them is, turn off the lights that you don't need, close the blinds, etc. The other is better lighting in the outdoors. So if you have a look at a lot of modern lighting, street lighting and lighting often around the Monash campus as well, you'll see that the lights are kind of boxy, and that's so that the light that comes out from those lights is all directed and reflected downwards, rather than the more traditional, sort of circular lights, which throw a lot of their light upwards. So there's certainly things that we can do to mitigate light in cities, and that should improve things with time, but it is still an issue. I think also for industrial applications, there needs to be a lot of care taken thinking about light as well. So for instance, there's a lot of people trying to push along, say, fracking in rural areas in Australia, and they often have gas flares associated with them, and those gas flares should be shielded appropriately.
Yeah. That's a really good point as well. There is currently a movement of Gamil means no not to promote, but I will, like fracking that has been approved across Gamilaroi country, and this is quite close to dark sky heritage areas, particularly is it Warrumbungle National Park, near Coonabarabran Siding Springs Observatory, where a lot of this fracking has been approved. And this is, it's not only leading to issues in light pollution, but also environmental destruction. So this is light pollution. It's like an interdisciplinary issue that you can definitely have a lot of people from different areas come together to try and solve, because it's it affects animals, it affects Indigenous Australians, it affects the lighting industry, and you can really and astronomers, and so you can really come all together and come up with a solution. But yeah, as Michael said, smart lighting choices, directed lighting, minimizing spill, all those sort of moves.
If people want to influence or attempt to influence groups or individuals, is there a particular way of targeting and getting that? It's pretty hard for an individual to influence what a new industrial site sets up. What are the ways of influencing people?
So I mean, there is the International Dark Sky Association, which does identify issues that affect the night sky and tries to coordinate on these issues. There's a lot of design standards that come out in Australia, some of which are related to light pollution. And often it's a case that some of those standards are mandatory, but others are more sort of recommendations rather than being mandatory. And obviously tightening up some of those design standards so that they're actually mandatory rather than merely strong suggestions would obviously help matters considerably. So talking to politicians, etc., lobbying, informing various inquiries on various regulations would be a key part of that.
Question 4. Can you give an example of a phenomenon that spans several generations between sightings and an associated Aboriginal or Torres Strait Islander story used to keep that knowledge alive?
Yeah, so an example which highlights longevity of oral traditions is it's a Yolngu story, so that's up from Arnhem Land, and it's a descriptor of, well, I'll highlight the story in a quick version because I think story is really important, and I don't usually like to separate telling about the knowledge without including the story. But it talks about two brothers who are going out in their canoe to go fishing and are struck by a pretty severe storm. And so their boat capsizes and the older brother is able to save his younger brother, but is unable to save himself. And when they return, well, the younger brother returns back to his community and they ask what happens. He explains the older brother's sacrifice, and they perform a ceremony to commemorate his memory and his contributions. And it is said at the time of this ceremony that this bright star emerges in the banks of the Sky River, which is the Milky Way, between the pointers of the constellation Scorpius, between Shaula and Lasath, which are the stars at the end. And so this is a very common sort of notion as well in Indigenous communities, because a lot of, instead of there being a massive focus on constellations as being the important thing, a lot of importance and significance is placed on individual stars. And usually for different communities, it'll be attributed to some important historical figure or member of their community. And so to see this bright star emerging after the brother's sacrifice, they instantly attribute it to being the brother's, the brother essentially having passed up into it's sort of like the afterlife. It's hard to explain, but it's sort of like that creation, the creation story relative to that community. So what's interesting about this, the location of this particular star, is that this is also something that was seen by ancient Chinese astronomers, and they dated it in the year of approximately 2000. I've forgotten the specifics, and they think that it's a supernova occurrence. And so if this happens to be the same object, it's a great example of a story that has been passed along for 2000 years. There are other stories which stretch back around 10 to 13,000 years regarding a specific placement of stars in the sky, because as astronomers know, we have our sky has this, well, our our Earth has this precession cycle, and so our view of the night sky changes over this cycle of about 26,000 years. And so 13,000 years ago, you're looking in a different part of the sky than what you are now. And that's just because of our axis and how we're spinning around it. It's sort of like a spinning top where it slowly changes where it's facing. And so we can use these features and geological features that are described in the stories to link up and date back the age of certain traditions. And so, for example, this is one that has a very long age. And then a final example is there are different descriptions of fire falling from the sky as well, in particular in sort of central areas, communities. And this fire from the sky is what we think to be something like a meteorite falling. And what's interesting is you can take these stories from these communities and essentially go out into these areas and have found meteor crater impacts as well. So then we can try and date them back. So there's different ways you can try and validate the longevity of these oral traditions. Yeah.
Thanks, Krystal. A quick question back to the light pollution. Does the use of LED lights, has that made any difference?
I don't think it's made a massive difference. There's some pros and cons with the use of LED lights. So for instance, for amateur astronomers, they can use a sodium filter to reject light from sodium lights, those distinctive orange lights, whereas a lot of the LED lights now have a much broader, white spectrum. So, that's sort of a negative for amateur astronomers with telescopes. And obviously the LED lights can be a lot brighter in some instances. I think it's probably on average a bit neutral. The LED lights can be somewhat brighter, but then also they're often used with the proper housings that let less light up into the sky. So we'll wait and see, I guess.
Okay, thanks, Michael. Next one is from Kim to Krystal. With such a diversity of Indigenous peoples, do they still share their stories of the sky today?
Yeah, definitely. So although effects of colonization have been pretty devastating, a lot of this knowledge is continuing and still existent. So it's good to think about Aboriginal culture not as some past thing, but as still the world's longest continuing culture. So a lot of this information stories still belong in community and also belongs in written records since colonization. And what's interesting is a lot of these stories will tend to be quite similar based on location as well. So you can see that there is this information exchange between groups over time. And one thing I like to highlight as well is the multilingual nature of Aboriginal groups, particularly before colonization. It was very important to be able to trade and communicate with different communities, and these trade networks were very vast and can spread across from one coast to the other coast. And so to be able to do that sort of trade, you would need to be able to communicate in different languages. And so to be fluent in, like, say, 5 or more languages apparently was quite common prior to colonization, because there is just this crazy diversity of different languages around you. And usually you would learn a lot of that knowledge in those languages. So there is still ongoing information, and there is a fascinating way of it being exchanged.
Thanks, Krystal. I'm not sure how many questions we have time for, but there's certainly at least one more left. In regards to teaching the concepts in, say, the high school setting, what do you recommend in terms of ensuring that we are doing so in a respectful and appropriate manner? I'm assuming this is in regards to any Aboriginal and Torres Strait Islander stories.
Yeah, so I think an important thing is, I know that there was updates to the curriculum in the last 2 years that were driven by a large working group to make sure that there were modules available at years 5 and year 8 for teaching Indigenous knowledge. And I know that the people who worked on these things wanted to make sure that the amount of resources and information they had included was enough for people to be able to communicate about these topics effectively, because they didn't want to scare any teachers off away from feeling they couldn't touch these topics. So I would start with a lot of those curriculum modules, even if you're not in that same year level for year 5 or year 8, it's probably a really great resource to help give that information along. And I know that there are also, there's been a lot of work into looking into how to most respectfully deliver this type of information in the classroom as well. So Angela, do you remember? I know this is the sort of stuff that we do include on our website because we want to aim it at teachers to make sure educators can engage with this content in a way that they feel comfortable with and supported with, and yeah.
And and that's why we needed a new website. So the curriculum material is at the Australian curriculum level, so that then has to be adapted to each state's. I actually find those pages, those government pages, super hard to navigate, but I promise, excuse me, there is maybe in excess of 120 examples, and hopefully if you have experience, you're an experienced teacher, you can get all the bits and pieces you need off that website. I can't speak highly enough of a short course that's available at the CCCA, which is the Centre of Cultural Competency Australia. It's run by Aboriginal and Torres Strait Islander people, and they have developed a something like 10 or 12 hour set of modules that you can just sign up and do online. There is a fee, I think it's about $190, and you get access for 6 months. I think that was really good, and it gives you a great basis. If you're looking for something which is just getting familiar with some background concepts and some ways to speak and relate professionally, I guess, and respectfully, then the series, The First Australians, is a documentary series that's often on SBS and is an amazing resource. It's about 7 hours. The material won't necessarily be suitable to show students, but it's fabulous for giving basic competency for teachers in that space, or anyone. We use it with our students. Okay, last question. Is there anything happening in the world of astronomy right now that you're excited about? More specifically than this, the one in an 800 years event? Is there new inventions? What are we doing in astronomy that's really exciting?
It's a great question. That it's a sort of a how long is a piece? How long is a piece?
Give us a couple each.
So I think a big theme that's been happening with my colleagues at Monash that's really exciting over the past 5 years or so is the growth of astronomy beyond light, exemplified by the detection of gravitational waves from merging black holes, and the discovery of those gravitational waves, the Nobel Prize for those gravitational waves, the discovery of new black holes being formed, of black holes merging together. And so that's been probably a huge theme at Monash in particular over the past few years. But there's so many other things that spring to my mind. Looking at planets in formation, again, something that my colleagues at Monash are very much involved in, where you can now, with the ALMA telescope, see such detail that you really can see these protoplanetary disks and the planets forming. And then I think the third one that I'll sort of highlight is the new facilities that are coming online. There's the James Webb Space Telescope, which is going to be launched in the next year or two. That's going to be amazing for my work. The Australian Square Kilometre Array Pathfinder, which is producing data right now. And that is going to open up the radio astronomy sky for Australian astronomers in a way that hasn't been possible before. And I'm really looking forward to getting students involved, getting their hands dirty in that data. Hopefully Krystal included in that contingent of students mucking around with that exciting new radio data.
Fingers crossed.
Krystal, what about you?
I would like to highlight from an Indigenous astronomy perspective, just how I know over time a lot of this information has felt very inaccessible, and I've been asked over the years as well about things like books. It's particularly for things like kids, for them to be able to read something and engage with this sort of information in a way that is a lot easier to understand than some of the more archaic stuff that we have. And so I just know a lot of people in this field who are producing things like children's books. For example, Corey Tutt, who is the amazing creator of Deadly Science, which is a fantastic initiative of getting not only just books to Indigenous students across Australia, particularly in remote communities, but like telescopes, amazing scientific resources, and getting kids enthused. I know he has a children's book coming out. I have one that I'm working on in the future. I know that there's academic textbooks, and there's novels that are aimed at kids or teens and young adults. So I think that I'm excited about a lot of that in terms of accessibility, in terms of knowledge sharing that's about to occur. So yeah, that's mine.
Great, thank you. There's no questions left, and we have literally got 30 seconds to a minute left. So thank you very much, all of the alumni that came and joined us today. I hope that you learnt some fascinating facts about astronomy and the night sky. Thank you, Krystal, and thank you, Michael, for joining us today. And thank you for our wonderful administration staff hiding in the background there, Claire, Michaela and Udi, for organising everything, for wrangling both Zoom and the questions.
Was tonight's talk. Now we'll ask Mr. Stevens up.
Concentration in that field.
Excellent, it's working on it. Well, good evening everyone, it's good to see a lot more people coming back here for our meetings after a fairly long layoff. For those newer members, I'm Mark Stevens, Society Vice President, and each month I present Sky for the Month. Just a little bit of overview on what's happening in the next month in the skies for your viewing pleasure. So for January 21st and February, I go part way into February because the next meeting is about halfway through. Some of the highlights that are happening over the next, 4 weeks or so is on the 21st, which is tomorrow, you've got Mars, Uranus to the northwest of the moon. Now, you can't see Uranus with your naked eye. So if you look, you'll be able to find the moon, you'll be able to find Mars. If you get them in a pair of binoculars, you should see a faint little dot between them. It's about equidistant between them. That's Uranus. Nice little conjunction tonight actually, which speaking with Greg, we'll probably put the scopes in the observatory on, between Mars and Uranus. It's close as they get, about 11:40 for the night owls. Comet 2019 Atlas, 2.4 degrees east of Alpha Centauri. Alpha Centauri is a pretty easy one to find. So on the 24th of this month, that comet is in that vicinity. It is about 10th magnitude, so you'll need a telescope to see it. But Alpha Centauri is pretty easy to find, so you might be able to see it. Also on the 24th, you've got Mercury at its greatest elongation east. Now, because both Mercury and Venus are inner planets, from our perspective, they circle the sun, and so pretty well they go everywhere with the sun. So when the sun sets and Venus or Mercury is still up, it's because they're moving away to the side of their orbit. And the furthest they get away is their maximum elongation, or what's known as the maximum elongation. So probably the best time to have a look at Mercury on the 24th of the 1st. Should be in the western sky, not sure how low it is. Saturn and Jupiter both having a conjunction with the Sun. That basically means they're hiding behind the Sun, so good luck viewing them. Moving into February, Comet Atlas is about 0.6 degrees southwest of Gamma. That's actually Triangulum Australis. And when I put the sky up, I'll show you where that is. So it's another one that's fairly easy to find. So those with a reasonable telescope hopefully should be able to find, perhaps have a look at that comet. Meteor shower, the Alpha Centaurans commences on the 31st of the 1st, runs through till the 20th, with the maximum event occurring around about the 8th of the 2nd, with about 6 meteors per hour. And on the 9th of the 2nd, Mercury is at inferior conjunction. So as you can see, it doesn't take Mercury very long to go from as wide out as it can be to conjunction with the Sun. So the sky, this is January night sky looking to the south. If you'll go out there tonight and actually check all of this out and make sure I'm right. Some of the more interesting things, up here you've got what's called the ghost of Jupiter. It's actually a planetary, what's known as a planetary nebula. For newer members, that's a nebula that's formed when a sun ends its life cycle and it squishes right down and then it sheds all of its outer layers. What that particular one has done is it looks very similar to Jupiter in shape and appearance. It's just not quite as solid as Jupiter, and hence the ghost term. It's actually quite an easy one to find. You've got the Eta Carina Nebula. This is the Milky Way here, so when you look up, you can sort of see the Carina, the nebula there. There's a couple of nebulas there actually. You also have the large Magellanic Cloud, which contains the Tarantula Nebula, which is a bit of a favourite one for the astrophotographers. And you have access to 2 globular clusters. Now, Vega Centauri may be just a little bit close to the horizon to see, but 47 Tucano is almost as good, and it's a little bit higher. Looking to the north, what we have, probably the biggest one there, or the one everyone looks for there, is M42 in the Orion Nebula. And last week at the public viewing night, I had a couple of people asking where was the Horsehead Nebula and the Flame Nebula. This is the belt of Orion. You have Big Tarka, Alnilam and Alnitak. You've got the Horsehead Nebula there and the Flame Nebula just below it. But talking to Greg, you need a special filter on your telescope to actually see the Horsehead Nebula. But camera will see it if you're good enough, if you're a better astrophotographer than I am. Other objects, you've got your Pleiades here in Taurus, along with your Hyades. These are open clusters, and a couple of other open clusters around about. What are the planets up to this month? Well, as stated earlier, Mercury is now an evening object. So you can probably see it now if you had a good view of the western horizon. Reaching its greatest elongation on the 24th, and then heading to inferior conjunction on the 9th. Venus, if you want to see Venus, you'll need to get up early in the morning before sunrise. It's quite a bright object. You shouldn't have any problems picking it out. Later, middle to late February, it starts to move into superior conjunction, which means it's on the other side of the sun. And once it moves there, you'll obviously not going to be able to see it. Earth, we passed the solstice, the days are getting shorter, and on the 2nd of January, we were at perihelion, which is the closest approach to the sun, which occurs pretty well every year at this time, which is why your southern summers are a bit warmer than your northern hemisphere ones. Mars, still visible in the northern sky. It's in Pisces but moving into Aries. It's past its opposition, so it's actually getting much smaller now. This is a non-opposition year, so we won't be able to see it in opposition again until later in 2022. It's still viewable, but it's not a lot of detail and much smaller than it was. Jupiter and Saturn, both below the horizon, heading towards their conjunction with the Sun, and probably a month, 2 months' time, they'll be morning objects for those who are pretty keen to see them. Uranus, still in Aries. I haven't changed that bit on this slide since I started doing these presentations. It's pretty much going to stay there until 2024, and then it might move into Pisces or something. On the 24th, Mars and Moon will be about 4 degrees apart. So a pair of binos or a scope with a good field of view, so a fairly low powered eyepiece, and you should be able to see a little dot in between them, and that's Uranus. So it's a bit of a conjunction there to have a look at. And as I stated earlier, Uranus and Mars are in conjunction later on tonight, so we probably have the scopes on them. Neptune in Aquarius. They haven't even put the date there, it's going to be there for a while. These aren't exactly the fastest moving planets. Fairly low on the western horizon now, after twilight, so we're probably not likely going to be able to pick it up and get lost in the twilight. Appearance of the planets. Mercury, there must be an awfully big telescope to get them that size. I've had a look at them through my telescope. They're not much more than a dot, although you can pick that it's a crescent or gibbous form. When it's at its greatest elongation, it's kind of side on to us, if you like. So we can see the back that isn't facing the sun, and we can see the front that is facing the sun, and so you get half a disc. Venus, well, it's a morning object, so it's on the other side of the sun. So if you actually look at the way these are lit, this is an evening object approaching us, and this is going away from us. So the shadow is on the right, it's morning. The shadow is on the left, it's an evening object. Mars, all right, you can see the shadow on the left there. It's just, don't normally get the shadows from outer planets. It's just because Mars is only half an astronomical unit away from us, so we can actually see a little bit of the back of it. Saturn and Jupiter, still fairly spectacular, particularly once they come out of conjunction. Won't be able to see much until then. And Uranus and Neptune, fairly featureless, particularly through telescopes, unless you have access to Hubble. And even then, I think they're pretty uninspiring. The other stuff, as mentioned earlier, Comet Atlas, about 10th magnitude and currently in Centaurus, and it will, as the month progresses, move into Triangulum Australis. I said I was going to point that out when I was looking at the sky. Probably go back to it if you like, after the end. Meteor showers, the only one, there was one earlier this month, it's already gone. The Alpha Centaurans acting from the 31st to the 20th, with a maximum hourly rate of 6 around about the 8th of the 2nd. Alright, these are the minor planets. Essentially read that as asteroids. Okay, these are the minor planets that are in opposition, and if you look down here you see their magnitude. The naked eye can see about 5th magnitude. My naked eye can see about 4th magnitude. Alright, a lot of them are in Cancer and Gemini. Probably the best way to try and find these would be to take a series of photos over a couple of nights and pick out all the dots that move. Alright. Pluto in Sagittarius has been there for a while. Put a telescope on Sagittarius. If you can pick out which one's Pluto, you're doing alright. It is moving into conjunction with the Sun on the 14th, which has already moved into. And for those that are really interested, it'll be a morning object for a while. And continuing with the solar system tour, I'm sorry to all those who missed the first day of 7 planets, but with the demotion of Pluto, Neptune became the furthest planet from the Sun. It was named for the Roman god of the sea, largely consists of hydrogen and helium, but like Uranus, contains a lot of ices, water, ammonia and methane. And because of the large amount of methane believed in its upper atmosphere, it gives it its blue colour. It has a diameter of 49,528 kilometres. So as a comparison, Uranus is 51,000. There's 14 moons that they know of, or found so far. Probably got a few more rocks circling it. and like all the other gas giants, it does actually have a ring system. And distance from the sun, who can imagine that number? So I'm not even going to read it out. Probably easier to think of it as 30 astronomical units. So the Earth is 1 astronomical unit from the sun, so Neptune is 30 times as far from the sun. And its orbital period is 165 years. So it's not too many people around have actually watched it do an orbit. Alright, best viewed in opposition. Not a lot of detail, but it's got a bit more than Uranus. It does have a bit of a band system like Jupiter, but not quite as distinctive. And it also has a dark spot. And that's its version of Neptune's red spot. It must be some internal heating. Obviously has the band system, which is usually indicative of some form of heating, creating motion and movement within its atmosphere. You won't see it like that through a telescope. All you see is a little blue dot. Tonight's information presented came out of Astronomy 2021 by Wallace Dawes and Northfield. I know Simon up the back there has still got copies available for those who would like your own copy. And the Neptune image was courtesy of NASA. They rang them up, they sent it to me personally. It was actually taken by Voyager 2. That should get in the way of the story. Any questions? I'll go back to the second one there and just point out where, righto, triangular australis is this one here. Can be found fairly easy because it's right next to what you probably know as the pointers, Alpha and Beta Centaurus, Southern Cross. So this is where that comet will be. Okay.
The comet, how long, like is it there all night, sort of all?
It'll be there for most of the month.
But all night, any particular time of the night?
Apparently it's heading away. It's heading out. It's around 10th magnitude now, so it's definitely a telescope object. Heading away now, so I don't think that's going to be around for much of the rest of the year. But I was reading somewhere, not sure, I have to check it up, but apparently a new one has been found that is on the way in, and I reckon it'll be quite specky. So once we get more information on that, we're on site for the month. Okay, thank you.
Okay, well with that we'll break for a tea break now, and as I said, after the tea break you have a choice. You can either come back in here and see the videos, or you can go down to the observatory and maybe Mark will be down there and show you some of the things that he just showed. And feel free to move from one to the other throughout the evening. Let's see, it's 9:30 on the clock there, so we'll have a tea break until 9:45, and at 9:45 I'll start the videos on in here. Okay.
So, did anybody get some photos of the conjunction with including Mercury there? What did you say again?
No, I haven't got it actually.
Sunday, it was clouded out.
Yeah, no, I haven't seen any.
They're obviously a bit further apart, but that's where Pluto was a week ago down there, and up there, Mercury.
This is what Jupiter and Uranus. Oh, Jupiter's happened.
And Mercury a week ago.
Yeah.
They're a bit bigger as a triangle.
Yeah, I think the problem with Jupiter and Saturn at the moment anyway is they're right down in twilight.
Yeah, that's what I'm saying, it's where Mercury was a week, last Monday, I think it was.
It's
8 days ago.
It's funny when you start tracking or keeping and trying to keep up with Mercury. It only takes 22 days to cover a quarter of its
So I look at the set
So
time,
it's-
it's up and down like.
Well, you saw it there, you know, only about, what, 2 weeks it went from basically the location to Mercury conjunction, so it's a fast one.
Hi everyone. After I was asked to do this segment more than a year ago, President Peter generously commented about my expanding our horizon, and I hope that has happened a little. For 2021, I'd like to hand over to the next generation of speakers, and I am ecstatic that an awesome presenter steps up to the platform. I shall briefly introduce him. The amazing Ethan Murphy has had an astronomical time. At around 1 year old, when he knew about 4 words, he pointed to the moon and said this. Then, first light on the 15 by 70. He's played with various prisms, gratings, spectroscopes, an MPAS moon-watch telescope, and produced a poster of his own experiment at a science fair. Here he operated these maquettes for himself from the Shrine of Remembrance. Next, he went to watch the launch of the InSight probe to Mars and visually observed Comet Lemur. He's built uncountable Lego rockets and spaceships and remote control vehicles. Ethan wrote another science fair experiment and did a PowerPoint presentation on Zoom. The parents expand his horizon also by placing him in a bilingual school. Ethan recently learned Spanish, which suits where they live in the States. He now reads Spanish books and wrote this illustrated space adventure story sent to Spain. So here's Ethan's PowerPoint presentation for you in English and Spanish. To our wonderful audience, I clear off and hand over to the next generation. Ethan Murphy.
Libro informativo sobre vehículos volantes, escrito por Ethan Murphy. Informative book about flying vehicles, written by Ethan Murphy. Introducción. Si quieres aprender sobre los aviones, helicópteros o drones, este es el libro correcto. En este libro aprenderás cómo vuelan los aviones, qué son los diferentes tipos de helicópteros y para qué se usan los drones. Introduction. If you want to learn about planes, helicopters, or drones, this is the right book. In this book, you'll learn how planes fly, what are the different types of helicopters, and what drones are used for. Capítulo 1. Los aviones vuelan porque el hélice del motor lo propulsa hacia adelante. Después el avión se eleva en el aire cuando el aire da ala porque la parte de arriba del ala es curva, así que tiene más distancia que recorrer, así que va más rápido y hay menor presión. Chapter 1. Planes fly because the propeller or motor propulses them forward. Then the plane elevates in the air when the air hits the wing because the top part of the wing is curved, so it has to go more distance, so it goes faster and there's less pressure. Capítulo 2. Los tres tipos de helicópteros son cuando hay un rotor principal y un rotor pequeño atrás. Cuando hay dos rotores principales, uno enfrente y otro atrás, y el último es cuando hay dos rotores principales, uno encima del otro. Chapter 2. The three types of helicopters are when there's one principal rotor and a small rotor behind it, when there's two principal rotors, one in front of the other, and the last one is when there's two principal rotors, one on top of the other. Capítulo 3. Los drones se usan para muchas cosas y aquí hay tres. Una de las cosas que hacen los drones es fotografía, otra es entrega y el último es vigilancia. Chapter 3. Drones are used for many things, and here are three. One of the things that drones do is photography, another delivering, the last one is security. Conclusion. Ya que sabes sobre cómo vuelan los aviones, qué son los diferentes tipos de helicópteros y para qué se usan los drones, podrás hacer cosas como aviones de papel y cosas así. Conclusion. Now that you know how planes fly, what are the different types of helicopters and what drones are used for, you can make stuff like paper airplanes and stuff like that. Todo sobre el autor. Mi nombre es Ethan Murphy. Me gusta mate y lectura. Vivo con mi mamá y mi papá. Mi pasatiempo es jugar videojuegos y he hecho libros de ajedrez, tectónicas, videojuegos. Tengo 7 años y vivo en Palo Alto. All about the author. My name is Ethan Murphy. I like math and reading. I live with my mom and my dad. My hobby is playing video games, and I've made books about chess, tectonics, and video games. I'm 7 years old and I live in Palo Alto.
Have you ever wondered why mirrors appear to flip things horizontally, but not vertically? For example, this piece of paper that says food now says doof in the mirror, with backwards letters of course, but they're still right side up. How would the mirror know the X direction from the Y direction? Another example, if I raise my right hand, the mirrored me raises her left hand. But if I put my hand up in the air, she also puts her hand up, not down. So what's going on? My first knee-jerk response is that our eyes are horizontal in our heads. But the problem with this hunch is that if you close one eye and look in the mirror, go ahead and try it. The text still reads backwards. Let's look again at the word food. When I read it, it's facing me and I see food. But when I turn it toward the mirror, wait a minute, I turn it. The mirror is reflecting it backwards because I am presenting it backwards. Think of it this way. If I look at the word, it is facing me. When I look at it in the mirror, I turn it away from me, and in doing so, I flip it horizontally. That's why it appears horizontally flipped or backwards. What if instead I flipped it away from me like this? That's a vertical flip, and now the word is flipped upside down. It still reads food, F-O-O-D in the correct order, but now the letters are vertically flipped. So if I'm doing the flipping, then the mirror is not. Take an arrow and point it to the right. The reflection in the mirror goes to the right. Point it up, it goes up. Left, it goes left. Down, it goes down. Forward, it goes... Wait a minute. If I point the arrow forward, the reflection goes backward. So the mirror is flipping the image, but it's flipping it in the Z direction. That's what's causing all of this confusion. When you look at your reflection in the mirror, it almost looks like you've walked around to the other side of the mirror and you're facing yourself. Hey Meg.
Hey.
What side is my right hand on?
My left side.
What side is my left hand on?
My right side.
Perfect, just like a mirror. But there's one problem. Let's take a closer look at our mirrored hands. Mine says R,
but mine says L.
In a mirror image, her hand would say R backwards. To get Meg's hands to look like this, I'd have to flip her image horizontally. But we said that mirrors don't flip horizontally. So that's where the flip in the Z direction comes in. If I could take my body and flip it through itself in the Z direction, I would get my mirror image. I know this was easier to see with an arrow, but I can also show it with a left-handed glove. If I hold it out in the Z direction, flipping it front to back would be the same thing as turning it inside out. Then it would be a right-handed glove, and it would fit on the right hand of the me in the mirror. All I did was flip the glove front to back. So why do we think things are horizontally flipped when they're really not? Well, consider our daily experiences. Most of the words we see in the mirror are on t-shirts. We don't think of them as horizontally flipped, but that's exactly what we do when we put them on. We flip them away from our normal reading position. Another part of the problem is that most of us are left and right symmetric. That causes you to see your reflection in the mirror as a normal looking person facing you. To face yourself without the mirror, you'd have to turn around, and that's a horizontal flip. It's hard to see what's wrong with this image unless you look closely. But if you turn to face yourself by doing a handstand, that's a vertical flip, and it's pretty obvious what's wrong with this image because we're not vertically symmetric. So to answer the question, why do mirrors appear to flip things horizontally? Because you flipped them horizontally. So the mirror is just showing you what you presented to it. Thanks for watching.
In the group who is always getting bitten by mosquitoes, because I certainly am. And science has shown that this is a thing, that mosquitoes are more attractive to some people than others. And the reason for that is at least partially genetic, which is why this video is supported by 23andMe, a company that reads sections of your genetic code and then helps you understand what's in there. Now, they've actually been involved in some research that has identified particular spots on your DNA that make you more or less likely to be attractive to mosquitoes. And in this video, I want to put that to the test. So I flew to New Mexico State University to meet Mosquito Man, Professor Immo Hansen. Hello.
Hello. We have a collection of lab strains.
Here he maintains colonies of many different species of mosquitoes. And one exotic strain, he actually feeds with his own blood.
No, I'm serious. These ones are made from my blood.
Really?
Yes, absolutely, yeah. I'm the only one feeding them. I can't ask my students, you know, that would be a nightmare getting permissions to
How do you blood feed them?
Well,
with just sticking your arm in?
I just put my arm in there and wait.
Is it psychologically itchy or?
No, it is really itchy. Yeah, and I'm getting, 25 bites or so right now.
Mosquitoes need our blood proteins to make their eggs, so only the female mosquitoes bite. The eggs hatch into these wriggly larvae, which develop into pupae before becoming flying adult mosquitoes. Then they once again seek out vertebrate blood to make more eggs. The whole life cycle takes just 2 weeks. But what I wanted to know is, am I a desirable target? How can we figure out if I'm attractive to mosquitoes?
Okay, we have a white tube, basically, which has a holding chamber. We put the mosquitoes down here. There's a little fan producing a draft, something like 4 meters per second. We're going to insert a bait into one of these chambers, and the green or the yellow one.
So by bait, you're saying me?
Yes, you, exactly. You put your hand in there. Would be good if you would rub your hand first, so if you're sweaty.
Get some oils?
Yes, right. That's where the good stuff is. Exactly. Aedes aegypti almost feeds exclusively on humans. They're really specialized on biting humans.
That's good to know.
Yeah. There's 20 mosquitoes in the holding chamber.
And they're going to decide whether to come and find me or go down the other side, and they find nothing.
Right.
We're releasing the mosquitoes.
Okay.
I see them coming. Oh, he's chosen wrong.
Do you see that? Man, you are attractive. I mean,
really?
Sorry. You are a strong attractant to mosquitoes. They all went in your direction.
None of them went the other way.
Yes.
This is amazing.
Now there's one.
I did not expect to have such a strong response. Like, you see all those mosquitoes.
Okay.
This type of test was actually used to discover that the basis for our attractiveness to mosquitoes is at least partially genetic. Researchers recruited 18 pairs of identical female twins and 19 pairs of non-identical or fraternal female twins. Then they used the Y-tube test to evaluate the mosquito attractiveness of each individual, measured by the fraction of mosquitoes who correctly flew to the arm of the tube where the twin was standing. What scientists found is that the mosquito attractiveness of twins is correlated. That is, the more attractive you are to mosquitoes, the more likely your twin is too. But that's not all that surprising and could be caused by environmental factors or a common diet, but comparing identical twins to fraternal twins revealed the correlation was higher for identical twins. This strongly suggests genetics influence how attractive you are to mosquitoes. Since the identical twins share more of the same genes than fraternal twins, this explains why their mosquito attractiveness would be more closely correlated, if it really is genetics that determines how much mosquitoes like you. With that last test, I was clearly attractive to these mosquitoes.
Yes.
Except we weren't comparing me to any other human, we were just comparing me to a control of
exactly, yes.
no human. So what if we compare myself with my wife Raquel? Normally I get bitten and she doesn't.
Okay.
So this should be a good test, maybe, to see whether under lab conditions
we can reproduce your...
We'll produce our anecdotal findings.
Yeah, exactly, your anecdotal evidence. They are a little...
Once again, preparing.
Okay.
Put hands in position.
Yeah, see, they actually start to wake up. They smelled something. Something's going on here.
Here we go.
Okay.
What are we saying? Whoa. I'm getting a good amount over here, but so are you. Let's see, I think I'm getting more. It looks to me like you got 3.
Okay, wanna stop the experiment right now?
All right.
Okay, now let's count. I think it's 7 on your side here.
5 in the holding.
5 in the holding. And quite a few on your side. So who gets bitten?
I get bitten.
You get bitten. In reality, we would repeat this experiment maybe 8 times or so.
Right.
And switching you guys around. But I think this is a good way to show how this works.
Okay, so that result was not particularly scientifically rigorous, but it did reproduce our experience in the wild, which is that I am much more attractive, well, at least when it comes to mosquitoes, than Raquel. But the question is, I guess, does this come down to our genetics?
Yeah, so we spat into some tubes and sent them off to be tested.
Right, and we were interested in 7 particular locations on our DNA, which were located in a 2017 study that involved 23andMe. So the way 23andMe works is when you sign up, you can opt in to be part of research. And 16,000 people agreed to be part of this study and rate their perceived attractiveness to mosquitoes. So then what the scientists did was a genome-wide association study. That is, they looked at all the DNA of all of those participants and tried to see if there were commonalities amongst the people who said they were attractive to mosquitoes and that were different to the people who said they weren't attractive to mosquitoes. And they identified 7 particular locations on the DNA, 7 single letter changes, which seemed to be associated with different levels of attractiveness to mosquitoes. So we have our results back, and do you want to see them?
I do. I'm very curious.
All right, let's pull it up here. Okay, so of the 7 locations that are related to mosquito attractiveness, it turns out we have the identical DNA at 4 of them. So you can rule those out, which leaves only 3 areas where we actually have differing DNA. So at the first location, you have 1 copy of a letter change, which actually makes you significantly protected from mosquitoes.
Oh, no way.
Yeah, it's associated with decreased attractive to mosquitoes. I do not have any letter changes at that location. Now at the second location where we differ, I have a letter change compared to you that makes me less attractive to mosquitoes, so more protected.
Interesting.
If you look at the significance of those 2 letter changes, yours is about twice as significant than mine, but still we both have a protective letter switch. So in the last SNP, we actually differ significantly, and I have 2 copies of a variant that makes me more attractive to mosquitoes. This was the only SNP which was associated with being more attractive to mosquitoes, and I have 2 copies of that change, and you have no copies of that change.
So that makes sense.
So overall, I would say our genetics really adds up here. And of course, we can't say that this proves that it is right, but it is definitely consistent with these SNPs actually being associated with your attractiveness to mosquitoes, and that's sort of borne out by our experience.
That's so cool.
Now, it's unclear exactly how these genetic changes might make us more or less attractive to mosquitoes, but it's likely that it has something to do with the odor or the volatile chemicals that our bodies give off, and due to the microbiome, the bacteria on our skin. One of the main signals that mosquitoes like to follow is carbon dioxide. So that means if you have a higher metabolism, or if you've just been exercising, or if you're a bigger person, or even if you're pregnant, you are more likely to attract mosquitoes. But mosquitoes are also attracted to some other volatiles that we give off, things like lactic acid, acetone, and ammonia. But scientists have also found some chemicals that repel or appear to impair mosquitoes' ability to find us. Those chemicals we naturally give off are octanol, nonanol, decanol, and 6-methyl-5-heptane-2-one. So why is this important? Well, the researchers estimate that our attractiveness to mosquitoes is about as hereditary as height or IQ. That is to say, genetics play a significant role here. So understanding that relationship is really important, especially when you consider that of all the animals, mosquitoes have the greatest impact on human health.
Are mosquitoes the worst animal of all time for humans?
Absolutely. Absolutely. There's no question about that. Malaria has killed more people than people have killed people. They are the most dangerous animal in the world.
By some estimates, mosquitoes have killed more than half of the humans who have ever lived. Now, that estimate has been debated and is likely too high, but even so, this year, over 1 million people will die of mosquito-borne illnesses. So if not half, certainly a significant number of humans have died due to mosquitoes, probably more than any other single cause. Which led me to wonder,
do you think humans may have evolved this trait to smell worse to mosquitoes as an adaptation to avoid the diseases? Or is it just by accident that some people are less attractive to mosquitoes than others?
That is a really good question.
And while we're on the subject of evolution, consider this. If you ever contract malaria, it actually changes your body chemistry to make you produce an odor that makes you more attractive to mosquitoes. Think about that. The malaria parasite has evolved so that when it's in its host, it makes the host more attractive to mosquitoes. Mosquitoes are the thing that transmit malaria. It's phenomenal. I mean, evolution is incredible.
So I always see people wearing those shirts that have a spiral galaxy on them and then a pin drop that says, "You are here," to mark where we think the location of the sun is in our own galaxy, the Milky Way, of hundreds of billions of stars. The question is though, like, how do we actually know that that's what the shape of the Milky Way is and where the sun is in it? Because we're trapped inside it. There's no way that we can get out of the Milky Way to take an image of it, because that's billions of trillions of kilometers that you would have to travel. It'd be like me plonking you in the middle of a forest and saying, map the positions of the trees in this forest. Oh, but you can't actually move to do it. How we see the Milky Way in the sky is just this band of sort of whitish, diffuse light along with all the rest of the stars. So how do we even know that the Milky Way is a spiral galaxy? So all the way back to the 5th century BC, Greek, Arabian, Persian philosophers all consider the nature of the Milky Way, that diffuse band of white across the sky. And a lot of them did suggest it could be made of many, many stars that were much further away from us than the other ones, because it didn't move relative to those. It was clearly in the background. And it wasn't actually until 1610 that Galileo Galilei, of dropping stuff off the Leaning Tower of Pisa fame, actually proved that this was true. He took a telescope to the Milky Way and showed that it was actually made of many faint stars, the light of which all combined to make that diffuse light across the sky. Fast forward now to 1755, and Thomas Wright and Immanuel Kant, i.e. the very famous philosopher,
You just casually cited Immanuel Kant.
both speculated that because you saw that diffuse band of stars in a strip across the sky, that the structure of the Milky Way was kind of like the structure of the solar system, where you had the sun in the center and the planets going round it. But instead here with the Milky Way, you just had a lot of stars all going around the central object, and that those stars were all rotating. And that was pure speculation then. They had no proof for that. They were basically philosophizing over it. But Kant also took one step further and actually said that the other fuzzy things that we see in the sky that people called nebula, they could also be island universes, as he dubbed them. All of these systems of rotating stars. Then by 1785, William and Caroline Herschel are the first people to try and actually map the Milky Way. And they did that by marking the positions of stars along various different lines of sight when they looked out into space. Now, to do that, they assumed that all the stars are the same brightness, so from their apparent brightness, you could tell how distant they were, which is not a very good assumption, we know now. They also were very limited by their telescopes. Back then they weren't great, and they also didn't understand that dust in space can actually absorb light from behind it. So if you look in a direction where there is lots of dust, then you're not going to see the many, many stars that are actually hidden behind that dust. So what they ended up with was a map where the sun was pretty much in the center and a very flat structure like what was seen in the sky. Into the 19th century though, telescopes have got much, much better with the Industrial Revolution, so much so that by 1845, Lord Rosse was actually able to resolve the shapes of those fuzzy nebula things in the sky and found that they had spiral structure. He even managed to show that in some of them you could resolve individual points of light as if they were stars themselves, giving more weight to Kant's original ideas that these nebula were actually galaxies in their own right, or these island universes as he called them. So this brings us up to the start of the 20th century, and this is where things start to all kick off. So in 1904, a Dutch astronomer called Kapteyn found that half of the stars in the sky were moving in one direction, and the other half of the stars in the sky were moving in another direction. Now that was not understood at the time at all, but eventually people made the connection between those results and the ideas of Wright and Kant back in the 18th century that the Milky Way was a structure like the solar system, but instead of planets going around the centre, it was stars rotating around some centre. So in 1912, Henrietta Leavitt was studying a type of star in our own Milky Way that we now call Cepheid variable stars. And these stars pulse in their brightness. And what she noticed was that how fast they pulse is directly related to how bright they are. So if you can measure how bright they appear in the sky, you then know how distant they are. And so this meant that we could finally accurately calculate the distances to things in the universe. And so every single distance measurement we now make in the universe is all calibrated on these nearby distant estimates using Henrietta Leavitt's law of pulsation time is proportional to brightness. So that in 1917, Shapley used this to try and estimate the size of the Milky Way. And he did this by using what we call globular clusters. These are clusters of about 100,000 stars in these big blobs that are very, very bright and very easy to spot and to see in the sky. And so because of that, they also have different types of stars in it that can help you calculate distances as well. And so he managed to estimate, using globular clusters that are also kind of insensitive to dust as well, that the Milky Way was about 100,000 light years wide.
It's 100,000 light years side to side.
And the sun was about 30,000 light years from the center, which he said was in the constellation of Sagittarius, because that was where the most globular clusters were found. Now that was much larger than people first thought because of the largest distance to a star seen, at least in the sun's neighbourhood, but that was because they hadn't took into account the fact that when you look to the centre, it's a lot dustier. And so for the first time we had a map of the Milky Way that put the sun not in the centre. In the same year though, Curtis was observing the Andromeda Nebula, as it was known back then, the things that were thought to be part of the Milky Way. And in it, he observed this brief brightening of a point source in it, which he said was a nova. Now, not a supernova like when you have a star that explodes and dies, but a nova is a little bit fainter than that. It's kind of a brief brightening of a new star. And so he said that nova was 10 times fainter than anything we'd seen in the Milky Way before. So if you use that to calculate the distance to Andromeda, you get something like 500,000 light years. Now that's much bigger than the estimate that Shapley had just made of the Milky Way being about 100,000 light years across. And so this triggered the great debate at the beginning of the 1920s. You had Shapley on one side arguing that the nebula were part of the Milky Way and the Milky Way was all there was in the universe. And then Curtis on the other side that was saying actually spiral nebula like Andromeda were actually galaxies in their own right, and the universe was much bigger than we had ever imagined. Now, the debate was eventually settled in 1926 by Edwin Hubble, who showed, using Leavitt's law, using the Cepheid variables, that the distances to Andromeda and other spiral nebulae in the sky were much larger than the size of the Milky Way, hundreds of thousands, if not millions of light years away. Now, Shapley originally called Hubble's result junk science until Hubble sent him a letter with all of his observations written down in it, and Shapley apparently responded with, "Here is the letter that has destroyed my universe." So through the 1930s, Hubble's categorizing all these brand new shapes of galaxies that we're seeing, including a lot of spiral galaxies. Combine that with the fact that in 1930, Trumpler studied open star clusters, slightly different to the globular star clusters in they're a little bit smaller, but still under the same principles that they're not as sensitive to dust. And he used that to actually categorize what effect dust has on starlight. And so with that, we were able to start making much more accurate maps of the Milky Way for the first time, and therefore the idea that the Milky Way might actually be a spiral in the same that we'd seen in other galaxies outside the Milky Way started to take hold. So in 1940, Jan Orr was studying the persistent hiss that was present on every single radio signal sent on Earth, and he realized that that hiss or signal was coming from space, and in particular from the constellation of Sagittarius, where the center of the galaxy was thought to be. So he then passed that observation on to Hendrik van der Hulst, who then predicted that hydrogen, again the most abundant element in the universe and therefore pervading the majority of the Milky Way, could actually produce radiation with a wavelength of about 21 centimeters, the microwave radio regime, where they'd been picking up this hiss, because of two very closely spaced electron energy levels in the atom. Now that's fantastic because, as I said, hydrogen is incredibly abundant, but also radio signals aren't sensitive to dust, so you can use them to see through the dust for the first time. So by 1951, this emission at 21 centimeters from hydrogen in the sky had actually been detected for the first time by Ewan and Purcell. Again, strongest in the direction of Sagittarius, but what it allowed was for Christian and Hindemann in 1952 to actually map the motion of this hydrogen gas in the Milky Way for the first time, revealing the spiral structure and also that the Milky Way probably had a bar structure as well in the very center. So once you had that map of spiral arms in the gas, you then knew where to look for the spiral structure in the stars. And so Morgan in 1953 managed to find evidence of a spiral structure in the positions of stars in the Milky Way as well. So now the spiral structure had been confirmed, work in the 60s turned towards that more interesting result that suggested that the Milky Way could have one of these bar structures. So there's a lot of work by people like de Vaucouleurs, Peters and Hammersley all investigating this bar, especially if they could find the stars in the bar as well. And so there was a lot of debate about where that bar was, how long the bar is as well, which actually kind of still continues to this day. So because of this, through the 1970s, people were still looking for a way to see the stars behind all of this interstellar dust. Yes, they'd use the hydrogen emission in the radio to see the gas structure behind the dust, but really what they wanted to see was the stars. Now, ideally, you'd do that with infrared light. Infrared light is not affected by dust, but unfortunately, it's also absorbed by the Earth's atmosphere, so you can't use a telescope from the ground to do that. Now, Georgeland and Georgeland in 1976, so they came up with the next best thing. They were going to use the hot, young OB stars that were incredibly bright, the brightest stars we knew of, especially bright in blue and UV wavelengths, to trace the spiral structure, because they weren't as sensitive to dust as the cooler, redder stars were. And so using that, they were able to find evidence for 4 spiral arms in the Milky Way. The Perseus arm, the Sagittarius Carina arm, the Scutum Crux Centaurus arm, and the Norma arm. Also at the end of the 70s, Vera Rubin was studying the rotation of stars in galaxies and actually found that the speed of their rotation couldn't be accounted for how much stuff you could see in galaxies. And actually there had to be this huge extended halo of matter that we couldn't see. And so this was the first evidence for dark matter, that galaxies are embedded in these dark matter halos. And the same should also hold true for the Milky Way. Now that's a completely other story about dark matter, but if you are interested in dark matter, I devoted a whole chapter to it in my new book that's coming out in September, but you can pre-order it now, and the link is in the description box below. So shameless book promotion aside, what this meant was that through the 1980s and the 1990s, a lot of the focus shifted towards measuring the total mass of the Milky Way and whether that mass could be accounted for by the amount of stars that we could see. In 1994, Hubble Space Telescope observations by Backel and collaborators showed that faint stars were nowhere near enough to make up the amount of matter we needed to explain the mass calculated by Zaritsky and collaborators in 1989 of 1.3 trillion times the mass of the Sun of matter in the Milky Way. So into the 2000s, we finally managed to launch an infrared space telescope so that we could see past the dust for the first time. And it meant that in 2005, the first conclusive proof that the entire Milky Way was a spiral galaxy finally came through. And that came from Benjamin and collaborators who, by looking at 30 million stars in the infrared, managed to show that the Milky Way had 3 arms and confirmed the fact that the Milky Way had that bar structure again. So through the rest of that decade and into the 2010s, the number of spiral arms in the Milky Way was heavily debated because there was lots of different conflicting results. Some showing the Milky Way had 2, 3, and up to 4 spiral arms, until eventually a lot of measurements were combined across different wavelengths, from the radio and the infrared all the way through to the ultraviolet, that eventually showed that actually the young hot stars that were very sensitive to the UV were tracing 2 spiral arms, and then the older stars that were more sensitive to the infrared were tracing another 2 spiral arms, giving 4 in total. At least that's 4 main arms. Now there are a lot of branches and spurs that come off those 4 main spiral arms, very similar to what we see in the galaxy Messier 101. In fact, the Sun is thought to be on the Orion arm, which is one of these little spurs and branches. So we can't put a definitive number on how many there are in total, but it means the general structure is agreed on. There's a bar in the center, there's 4 main spiral arms. All of that is embedded in a very, very low density stellar halo where you've got very few stars scattered over a large space, and then that again is then embedded in a much larger dark matter halo as well. But this picture could very easily change as new evidence comes to light. Such is the nature of science, as we've just heard, as theories evolve and change as new results pour in. Now, as we look towards the next decade, the future of this field definitely rests with the Gaia spacecraft. Gaia is going to make what we call a 6-dimensional map of the Milky Way. So you'll have the 3D positions in X, Y, and Z of 1 billion stars, along with the velocities in those dimensions as well. So the velocity in the X, Y, and Z direction. So that for the very first time, we'll not just be able to get a map of the positions, but also a map of the actual movement of all of those stars in the Milky Way as well. So the first of these maps is going to be released in 2022, and I, for one, am so excited to see the evolution of the Milky Way go from this static structure that we see in the night sky to having its dynamical nature revealed in all of its glory.